All right, so how's everybody doing? Any questions about what we've been talking about this last week or so? We okay? We okay with this? We're all good? Thinking about what we're going to be doing tomorrow, right? Okay, on some airplane going someplace. All right. Okay, so anyway, let's finish this thing off properly. The kinetic molecular theory of gases. I guess it looks like gases. There you go. This is nothing really new from stuff that we've already talked about. My phrasing is quite right there. The first thing about the kinetic molecular theory is gases consist of particles whose separation is much greater than the size of the particle. So let's just re-emphasize it for this chapter. Okay, so we got gases consist, yes they do, of particles. Okay, gases do consist of particles whose separation is much greater than the size of the particle. Should be made. There you go. Okay. All right, let's do something else here now. The particles of a gas are in a continual, random, and rapid motion. Okay? The particles of a gas are in continual, this over here a little bit better, there we go, are in continual, random, and rapid motion. Okay, and the total energy of the system is unchanged. We'll talk about that a little bit more too. And let's see, the average kinetic energy of gas particles is proportional to the gas temperature. Okay. Okay, the average kinetic, let me pull the board up here a little bit so I can write and you can see. The average kinetic energy, okay, of gas particles now, that said, I have to push the board down and draw another line. Anyway, it'll go up soon enough, so if you miss a word or two, you can just keep going. Okay. Okay, the average kinetic energy of the gas particles is proportional to the temperature. Okay. Yeah, we talked about that, you know, how as you put more and more, transfer more heat into a system, kinetic energy goes up, and so does the motion of the gas particles. Let me get out of the way of that thing. Okay, let's say all gases have the same average kinetic energy at the same temperature. All gases have the same average kinetic energy at the same temperature. Here we go up again. Okay, I'll keep it up there just a little bit while you copy that down. Okay, so a lot of the stuff we've already talked about, even from the start of the semester, when we talked about the gas state and all that type of business. And also we started talking about ideal gas. Okay, ideal gases, it's basically, we talk about the volume of the total volume of gas particles versus the total volume of the container. Okay, the container basically contributes most of the volume. Okay, so these gas particles, as you can see here, the separation is much greater than the size of the particle. So we're talking about little attractive interaction between gas particles. Okay, we can treat them as points without any mass, anything like that. But then towards the end of, in fact, by the end of this lecture, we will address the real physical properties of gases, okay, and how they do behave at high pressures. Okay. Now, there's a little plot here that I'm going to talk to you guys about for a bit here. And let's see how well I can draw this. And let me also give you guys a reference on this plot. Okay, this deals with molecular speeds. And yeah, you can look at this on page 208. Okay, no, actually, no, 205. This is a much better one to use. Okay, 205. And as far as the y-axis, that's going to be the number of molecules. Okay, and as far as the x-axis, this is going to be the speed of the molecules. Okay, and we'll talk about like 400 meters per second, 800 meters per second, and so on, 1,000 meters per second. Okay, meters per second. There you go. Now, if you take a gas like oxygen, and let's say at 25 degrees, this is just going to be an approximation here, but you're going to see something like this, as far as the distribution of the energies. Okay, not the energies, but the speed of the molecules, the distribution. Notice they're not all going at the exact same speed. There's quite a bit of difference in there, because there's going to be variations in the energies of these molecules. Okay, now right here, this is going to give you your average. Okay. Now the thing is, let's say this will be at, let's say, 25, let's say 0 degrees centigrade. Okay. Now as we increase the temperature here, like 1,000 degrees centigrade, we're going to see something more like this. Okay. Okay. And yeah, let's mark this as being O2. Now you can see what's going to happen here. Like the average speeds, of course, are going to be shifted up higher and higher, but there's also a broadening, okay, the distribution of the speeds as you increase the energy, or increase the speed, okay? Let's see. Okay, so let's make a couple of comments here. Move this over here. Okay, so let's say in graphs, okay, molecular speed, okay, peak is the most probable speed. Okay, so you can see the most probable speed would be like right here and right there. Okay. Yeah. Now let's see. For this, let's get to a clean board. So put this up. Bring this down. And let's move this over here. There we go. Get the cameraman alert. Okay. Okay, microphone's still working. We're going to talk about root mean square speed. Okay. Now, I just gave you that diagram up there. Yeah, let's put it up like this. Here's your root mean square speed, and it basically is calculated as free RT divided by the molar mass of the molecule, and the R value we use here is 8.314 joules per mole Kelvin. Okay, so we're not going to use the regular one. All right, now let's see. Let me just redraw that just a little bit. Okay, so here we go at the speed. As I said, right here would be your average speed, the most probable. Okay. Now, a little bit ahead of it, about right here, let's say, is going to be what we call the root mean square speed. And basically, the average speed is normally approximately 9/10 that of the root mean square speed. And the root mean square speed, basically, that indicates the speed of molecules that have the average kinetic energy. Okay? So this indicates, okay, the speed of molecules with the average kinetic energy of the whole sampling. Okay, that's called the root mean squared. And just an added note here would be the average speed is 0.921 times u. In other words, the root mean speed. Okay? So the average speed is always just a little bit below that one. All right? There we go. Just kidding, everybody. Loosen up here. It's only chemistry. It will pass. Okay, page 209 in our good book is going to be effusion and diffusion. We should also say confusion, too. Here we go. Effusion and diffusion. Uh-oh. All right, process of effusion. Okay, process by which a gas escapes through a tiny hole. Okay, in its container into a vacuum. Doesn't sound very exciting, but, okay. Person by the name of Graham did a study on this and came up with some good stuff. Okay. Thomas Graham. I'll make sure my camera's got enough angle to it. Okay. Excuse me. So Thomas Graham Okay, found that that the number of gas molecules gas molecules escaping per unit time is inversely proportional to the square root of the gas density. I can't push this up. Is inversely proportional to the square root of the gas density. So I'll put square root there, and up here, hopefully everybody can see that okay. And we're on camera too, that's good. So the square root of the gas density. Okay, so basically he's saying that the rate of fusion is inversely proportional to the square root, of the molar, of the density, but this is going to be directly related to the square root of the molar mass of the gas too, okay? So that is the initial statement here. Now how we use it is this way. Let's assume we have two gases. Okay, assume we have two gases at the same temperature and pressure. Okay, so we can have a line here. At the same temperature and pressure, in two containers, so you can put this on in here, in two containers with similar pinholes. Okay, so you got two gases, two containers, and the containers are identical as far as pinholes, and they're at the same temperature and pressure. Okay. If the rate of a fusion, that's an S, are R1 and R2, okay, and their masses, I'll just say masses, molar masses, are 1 and 2, okay? So define the rates as R1 and R2, okay? And the molar masses is M1 and M2. Then we come up with, make sure this is over far enough. That should be okay. Good. We're going to have R1 over R2 is going to be equal to the square root of the molar mass of 2 over the square root of the molar mass of 1. Okay? This is where this law becomes helpful, because if we know the rate of a known gas, like I'm going to give you an example here where we're using oxygen, then we have an unknown gas, and we want to find out what its molar mass is. Well, let's say we use oxygen here, and we know how the rates compare. So they've done basically a study with the unknown gas. They know how it compares to the rate of the oxygen gas, okay, going through this little tiny hole. Now we know the molar mass of the oxygen, but not the molar mass of the unknown. So you can see that what we can do is we can basically solve for an unknown using this equation here. And let me do that now. Let's see, to do this, I think I can, yeah, I'll try to squeeze it up here. I think I can do that. Okay, we'll see what happens here. And I'm completely over there. So, okay, an unknown gas composed composed of homonuclear diatomic. Is everybody okay with that, those terms, homonuclear diatomic? Okay, good. Okay. Homonuclear diatomic molecules. Okay. Fuses at a rate, okay, that, I have to get low on the board here, that is 0.3, let's see, get that big, 0.355 times the rate, okay, to be continued. I'll see you at the other end of the board here. Just keep writing. I'll catch up, or you'll catch up. Here we go. Yes, ma'am. I'm sorry? Homonuclear. Okay. Here's what we're doing. If you have, let's say, nitrogen monoxide. Okay, now there are two atoms there, right? So that would be a dinuclear, or, excuse me, it would be a diatomic molecule. Now the thing is, they're not the same atoms, are they? So the nucleus of both of those, they're different. So here we would say dinuclear, or diatomic if you'd like, it's probably even better. Diatomic, excuse me, I'm sorry. Russian trying to get through here. Okay, you would say dinuclear, or heteronuclear. I'm sorry guys, a little flustered, here we go. Okay, it's actually called heteronuclear. Okay, heteronuclear means that it's two different types. If it's like O2, that would be homonuclear. Homonuclear diatomic, okay? And it turns out we're going to be using oxygen, which is homonuclear diatomic, okay? Sorry to get flustered for that. Still early in the day for me. There we go. All right, so we left off with the word that is 0.355. Can everybody see that? Everybody? Okay. Let's come over here now. That is 0.355 times the rate at which oxygen fuses. Okay? At the same temperature. Now you can see the importance of talking about the temperature because, you know, temperature is going to basically talk about the kinetic energy as well as the speed of the molecule. So you have to make sure that everything is the same. All right. So what does this lead us to? We have calculate molar mass of unknown. Okay? Now the way we'll do it is this way. We'll have the rate of X over the rate of O2 is going to be equal to the square root of the molar mass of the O2 over the square root, here we go, of the molar mass of the unknown. Now something else we have here, this value, 0.335. Okay, so the rate, I should say Rx, is going to be equal to 0.355 times the rate of the oxygen, right? Is that okay? Okay, it is. All right, so if we're looking at these guys like this now, the rate of the unknown is now defined as 0.355 times the rate of oxygen over the rate of oxygen. And then we're going to have over here on this side the square root of O2, which is going to be 32 grams per mole. Okay? Bless you. Okay. Square root of the molar mass of X. Okay? Now looking at this now, we can see that what's going to cancel out is going to be rate of oxygen. So we're just going to be left with 0.355 is equal to, now we're going to have the square root of 32.0 grams per mole over the square root of mx. Now what can we do to make this really workable? What's a really fast way to take care of this? We got square roots on one side. Square both sides. Square both sides. He said gulping his coffee. All right, so we're right here, and if we go like this, square, square, that eliminates these radicals here. Okay, we have to square the 3.55. And let's see. Here we go. What that's going to give us is 0.126 on this side, and over here now we're going to have the square, excuse me, not the square, it's going to be 32 grams per mole over the molar mass of X. Everybody see that okay? Ready? Good. All right. Now let me just scrounge a little more board here. So let's rearrange this one here. So it's going to be molar mass of X is going to be equal to 32.0 grams per mole divided by, and it's going to be 0.126. So the molar mass of X is going to be equal to 254 grams per mole. Now how does that help us with our identification? Well, we've already identified the unknown as a homonuclear diatomic, okay, like O2, N2, Br2, Cl2. So what you could do is take 1/2 of that and see what element has an atomic mass of 1/2 of that, and then just double it, and that'll give you your homonuclear diatomic, and in this case it's most likely iodine. Okay? So how are you guys doing? All right? Okay, we got time left for everything. Okay, good. Okay, let me switch the camera here now, and you guys can call out for pizza while I erase the board or something. Now we talked about diffusion. Diffusion is actually, it's based on Graham's law. Graham's law is what I put up there for you. In fact, let me write that out. I just talked about it. Let me write it out for you, too, so you have it in your notebooks. All right, here we go. Yeah, we'll say that Graham's law, okay, so that will say the rate of diffusion Okay? Rate of diffusion of a gas, okay, is inversely proportional, okay, to the square root of its molar mass. Okay? Now, I had to erase it here because I wish this board would go up too, but just recall when you're putting all this together here, what Gran was saying was the rate is inversely proportional to the square root of the molar mass. That's good. But as far as how we use it, you take two gases, gas 1 and gas 2, you compare their rates, and then you can use this to calculate the molar masses. They're inversely related to the rates. Okay, that's how we basically use it. Okay? Now, we could also use it to come up with a rate that we don't know. If we have the molar mass of a particular gas, we can find out what its rate is too. But, you know, the real power of this thing is figuring out the molar mass of some unknown gas. All right, now as far as diffusion, I'm not going to spend a whole lot of time on that, just kind of show you that it is related to what Graham has done here. Process of diffusion. Okay, and it's fairly similar, okay? It's just the movement of one gas through another. Okay? And it's also described by Graham's law. Okay, which I just put up here for you. Okay, just the same thing there. And there's not a whole lot of difference. I'm not going to spend a whole lot of time on it, but just to say this. Molecules move at hundreds of meters per second, yet, you know, like one thing that textbooks always like to talk about, if somebody opens a bottle of perfume in a room or something like that, all of a sudden it doesn't hit you like that, like, wow! It's kind of like it takes some time. And if the molecules are moving at that kind of speed, why is it that we aren't all of a sudden, like instantaneously, you know, our noses are picking up all those wonderful aromas? Well, it's because we have a lot of collisions, like it's traveling through air, awful lot of molecules, okay? So there's a lot of collisions going on, too, which slow the process down, okay? And, well, yeah, if I give you this example here, it's absolutely no different from the one I just gave you before, except for this one here. They'll just, in the book they just talk about if you're looking at like two gases mixing in air, like you have ammonia and you have hydrogen chloride, okay? Well, it's going to be the same type of situation here. Okay, you're going to have your molar mass of your HCl, the molar mass of the ammonia, and you know, I think Graham's law of diffusion, I think, has a lot more, well, let's say a little more problem-solving interest to it. But anyway, that's it basically. Graham's law is the big one. Okay, the rate of diffusion, there it is. This is how you use it. Diffusion, okay. There are ways to measure this thing. Like when you combine, if you have like a glass tube, somebody can look through, and you just start bleeding ammonia gas in one side and HCl gas in the other, what kind of a product are you going to get, do you think, with ammonia and HCl? Have any thoughts? I'll give you a hint. It's ammonium chloride. It's a solid. And you can actually see a ring of it forming in the tube as it starts to, and you can see the displacement of the tube. They're diffusing at the exact same rate. It would be right in the center of the tube. Instead, it's over to one side. The thing is that the heavier a molecule is, the slower it moves, okay? So you can see between the two, we have ammonia, we have HCl. HCl is going to be heavier, okay? It's going to be moving slower. So you're going to see that ring is displaced over towards the HCl part. But that being said, what I'd like to do is finish this chapter talking pretty quickly, but not at a dangerous pace, about real gas deviations. Basically, deviations from ideality, okay? So we say real gases deviation. Okay, from ideal behavior. Okay, now in our last lecture, you might want to review that lecture because it's been a little while. We talked about the kinetic molecular theory of gases, and talked about how we treat gas molecules and gaseous atoms as nothing more than points in space, okay, and that the volume, let's say the volume of the container versus the volume occupied by the gases, most of you just think about the container almost as if it were empty, okay, that there's no interaction between gas molecules. Now, next semester, you guys going on to Gen Chem 2, you're going to learn an awful lot about interactions, okay, between molecules, intermolecular forces. And let me see, my mic is still working. But as far as the ideal gas behavior, we totally disregard that stuff. Okay, now what we're going to do is we're going to see what happens when basically non-ideal behavior is basically occurring. Okay, now we can take the ideal gas law and basically rearrange it. Okay, and this is for 1 mole of gas. And what we're going to get here is a 1, okay, unit value. Now, if we were to look at a plot of this, okay, on the x-axis, this is going to be external, let me pull the board up here, external pressure from the atmosphere, okay? Imagine again that we're in a cylinder. We have our contents, the gas molecules within the cylinder, okay, and a piston is basically being pushed down on it at 1 atmosphere pressure. Okay, we have 1 mole of gas in there. Okay, now the thing is we're going to see this kind of behavior. Let me put down some numbers here. Okay, this is going to be 200 atmospheres. This is going to be 400 atmospheres, 600, and 800 atmospheres. Okay, now up here, this is just going to represent this number here. And an ideal gas, regardless of the external pressure, is going to retain a value of 1. Okay? Now the thing is, we already see some departures from ideality. And just give me a half a second to find the page. I meant to open the book to this page when I started talking. And it should be in the very, very back. And it's not right where I thought it was. So just give me a second here. Sorry about this. My Lord, I might have been thinking about another book. Whoa! What's that? 215. I don't think so. Let me take a look there. Whoa! There it is. Okay, 215. Thank you very much. What can I say? Remember I told you guys that for an ideal gas at STP, standard pressure and temperature, that we had a molar volume, okay, so in other words, 1 mole of gas will be 22.4 liters, correct? Okay, now, actually, even at STP, if you look on page 214, they show you like helium, it's close, well, it's 22.435. We come down here to argon, and it's 22.397. Let's take another one. Carbon monoxide is 22.388. Chlorine, 22.184. Okay, the idea is they're very, very close, but they aren't right on the money. there's some departure from ideality that we're talking about here. And let's look at what actually happens here. Look at two gases here. Okay, let's put some more values up here, like 1.5, and down here we'll say this is 0.5. Am I still on the screen? Yes. Okay, carbon dioxide, what happens is, as you increase the external pressure down on the system, okay, we're going to see values like this now. It's going to come down, and then it's going to start taking off like this. Okay, this is for carbon dioxide. Okay, if we look at nitrogen, it also kind of curves down, and then it also goes up like this. Okay, now let's just look at this equation and figure out what could be possibly going on here. Why do we see increasing values? Okay, now one thing, for the increasing values would mean that, let's say the denominator starts having more of an influence, or let's say the numerator gets smaller. Does that sound about right? Do you give us a larger number out here? Yes. Okay. So anyway, so pressure and volume. Well, if we have gas particles in a container, let's say I can squeeze this little figure in here. What is it that results in pressure in a container? What is it that gives us this thing we call pressure? It's physically what's causing it. As far as gas particles, what? Gravity. I'm sorry? Gravity. No, not gravity, no. No. Think about this. Right? Okay. Monday morning, okay? You're still thinking about St. Patrick's Day, aren't you? No. No? Okay. That's cool, too. Anyway, as far as, think about that balloon, okay? Imagine a balloon that's got gas in it, and let's say, we carefully heat the balloon. What's going to happen to the volume? No, let's not use a balloon. Let's use a cylinder and a piston. Work on that. So it's constant volume, okay? Now, if you start heating that cylinder up, what's going to happen to the pressure? Is it going to go up or down? Think about what Charles said. It's going to go up, right? Why? Because the molecules are not only moving more, but the pressure is the result of the collision of these molecules against the vessel's walls, okay? And the more collisions you have, the higher the pressure, okay? So let's just say we have these molecules in here who are, well, at the beginning, for ideal behavior, they're just totally unaffected by each other. They're just zooming around, hitting the walls. But now let's just say that there actually is attractive forces that these gas molecules can feel, okay? So actually we got some of this kind of stuff going on too. We have molecules attracted to other molecules. That's going to kind of decrease those number of collisions on the walls, okay, because we've got attractive forces that are kind of, deviating from that. So what's going to happen is, as these molecules start to kind of sense each other and get attracted towards each other, P is going to decrease. Does that sound about right? Yeah, P is going to start to become less because there's going to be fewer collisions. So this number starts to get lower, which means this number here is going to start to get bigger. Now something else, volume. We're talking about gas particles as dots, as points in space, but in reality, they do have mass. They do take up volume, okay? So the thing is, we're talking about ideal behavior. We basically totally ignore the volume taken up by the gas molecules. We just, you notice in our homework problems, they always say things like, in a 22-liter container, they never say, well, gas molecules taking up so much of that space. It's always just the container is all that we're concerned about as far as the ideal gas equation. But now, if we start, let's say, reducing with more and more pressure here, these molecules are getting closer and closer together, and actually their volume is now we will now subtract that from the volume of the container, okay? We're now actually acknowledging that these gas molecules that are getting closer and closer together as we increase pressure on them, okay, now we have to say, well, we don't have just an empty container. Okay, now we got a container that's got stuff in it, And this is going to affect things. In other words, the volume is going to start to decrease. So both these guys start decreasing, boom, they start taking off. But the ideality now is disregarded. Okay? So let me show you what we do to correct for this. Okay, let me move this over here a little bit. There we go. Okay, going to check to make sure. You know, it seems like these morning lectures, the videos seem to at least go well. My evening lecture, I have a 2-hour lecture Monday and Wednesday night, and for some reason I always seem to lose my mic the last, I mean not lose it, but the mic goes out like the last half hour of each lecture. So I'm not sure why that is. I keep it charged. Okay, so we have PD is equal to nRT. There's our ideal gas law. But now let's look at the pressure and the volume and see what we do to basically, you know, account for reality. Okay? So it's going to look like this now. We're going to have pressure plus n squared A divided by V squared. Okay? N is just the number of moles, and V, of course, is the volume. A here is, call it a fudge factor, if you will. Call it a, no, van der Waals constant is probably the best. This would be on table 5.4 on page 216. I'll talk about this more in a second. Okay, so we've got that. Now what's going to happen here, this A accounts for the attractive forces. Okay? Attractive forces, okay, between gas molecules. Okay? So, this is just the straight pressure that we normally talk about, but this is going to give us a correction for the pressure that I talked about over here. Okay, now the next thing is we talk about is the volume. And to correct for the volume, it's just the normal volume V, the container, minus NB. Okay, now N is once again the number of moles. Okay, B is going to be our correctional factor for volume that I was talking to you guys about. Okay, so B here, okay, B here accounts, okay, for volume occupied. Okay, by gas molecules. Put this up just a little bit. Okay, so here's one correction factor. There's the other one, the A and the B. Like I said, if you look on to page 216, we can put that here, page 216, table 5.4. Okay, they will give you, in fact, let me just read a couple here for you while you guys are copying it down. Like for helium, the A is 0.034. Now, the units is atmospheres times liters squared divided by moles square. Okay? Sounds crazy, but the thing is when you put it into this equation, it does work out. Now, the B constant for helium is 0.0237 liters per mole. Okay, and then they give you all these other ones here. They give you carbon dioxide, the A and B values, ammonia, the A and B values, oxygen. Okay, so what I want to do is do a problem with you, so you can just see how to, I mean, basically it's just plugging these values into this equation and going with it. Okay, it can get kind of tricky if people want to, you know, when you get to P-Chem and they ask you questions like, you know, solve for the volume, you know, they give you all that kind of stuff. You got to rearrange and do all kinds of horrendous algebra to do it. But for the most part, it's just the way I'm going to do this anyway. on an exam, I'd give you a table, okay? In fact, I might even, yeah, I'll give you the equation too, okay? You can always look the equation up, right? Right? So, anyway, it's just basically plugging the values in and solving. So it's not a big deal. But the important thing is understanding what these mean, okay? And why we have this thing, which is called, I didn't give you the name of it, but I guess I should do that now. This is called the van der Waals equation. Let me put that up here. Just VANDERWAALS equation. Okay? So we have our ideal gas equation, and the van der Waals equation corrects. Okay? Now the thing is, this thing will kick in at higher pressures. Okay? Let's see. Let me go back to my problem here. Okay. All right. Okay. All right. Did you guys get this name down? Because I want to erase it now so I can put a problem up here. I noticed on the videos that when I erase something, it's a huge white spot on the screen, so I'm trying to clear that up a little bit. Okay, I'll read it to you first. If 1 mole of an ideal gas were confined to a 22.4 liter container at 0 degrees centigrade, it would exert a pressure of 1 atmosphere. Okay, so we already know that. Okay, getting back to the ideal gas equation. Okay. Use the van der Waals equation, table 5.4, to estimate the pressure exerted by 1 liter of chlorine, not 1 liter of chlorine, I'm sorry. It should be, left a word out of here. Okay, 1 mole of chlorine at 22.4 liters at 0 degrees centigrade. So what we're going to do is we're going to just take the chlorine gas. We've got the pressure, temperature. We can easily do this, but they say, well, tell you what, just take the parameters, but, plug in an A and a B. Put it into the van der Waals to see how much it corrects for what we originally have. Okay, and we're going to be looking here for the pressure, and normally our pressure would be 1 atmosphere from what they gave us. So we'll see how much it deviates. It's just one of these problems to kind of give you a sense of how far things can go off here. Okay, so let me write this up here. Okay, if an ideal gas, okay, were confined to 22.4 liters at 0 degrees centigrade, it would exert a pressure of 1 atmosphere. Okay, nothing new there. Now, what we're going to do is use the van der Waals equation Okay. Well, table 5.4, you can just write that down. To estimate the pressure of chlorine, 1 mole of chlorine, can get that down real quick, and I don't move the camera just yet. Okay, 1 mole of chlorine in 22.4 liters at 0 degrees centigrade. Okay? So like I said, we're just going to, plug in these values here. Now, here I'll say table 5.4, and there's going to be an A and a B value. So let's see, for A, what did I have here? Is it 6.9? Yeah, 6.49. Okay. I'm trying to get this right. And for B, the value is going to be 0.0562. Okay, and that's going to be liter moles. Okay, so it's just off the table there. That's page 216. Pardon me? Of course. Yeah. Unless you want to memorize all that stuff, but no. No, I've told you guys many times, I'm not impressed with memorization. I'm more impressed by people understanding how to apply this stuff, okay? Sometimes I tell you guys to memorize things like, a cubic centimeter is 1 milliliter, Yeah.
Are you just going to ask us to use that equation like on a test, or do we need to, like how would we know to use that equation unless you ask us?
Oh, because usually in these kind of problems it says something like, using the van der Waals equation.
Yeah.
Or they say under non-ideal conditions.
Okay.
I mean, there's this huge, hints on when to do it. And like I said, for an exam, I'll, give you guys a break and give you the equation, okay? So don't worry about that part of it. However, I might ask you, it could be a question about, A does what, and just know what A does. It accounts for attractive forces between gas molecules, and B, of course, accounts for volume occupied by gas. So the thing is to understand what all this is about. Anybody can, plug in the numbers, but it's the idea of understanding why we're doing this. That's huge in chemistry. All right, so let's see, to do this properly, I think I have enough room here. I might have to go on the other board. Okay, let's try it out here. Okay, to rearrange it, we'll have T plus N squared A divided by V2. And this is going to be V minus NB. And this equals RT. Okay, now we have to basically rearrange here and solve for the pressure. NRT. Excuse me? NRT. What do I have? Just RT. Oh, sorry about that. How's that? Good. Okay. Handwriting looks like heck. I almost said no. Okay. NRT, a little bit better. Okay, and then just rearranging it. You can try this at home, making sure it rearranges properly. NRT divided by V minus ND. Okay. Minus N squared A over V squared. Okay? Yeah. All right. And let's see what that's going to look like as far as the actual problem here. I think I can put this all here. P is equal to 1.00 moles times 0.0821 liter atmospheres over moles Kelvin times 273 K. Okay. Oh, I can't fit it all there. I'm sorry. I didn't read far enough ahead of the problem here. I can do this right here. Okay, I can fit it all here. So it's going to be P is equal to 100 moles times 0.0821 liter atmospheres over moles Kelvin, 273K, and then this is going to be divided by 22.4 liters minus 1 mole times 0.0562, that's going to be liter moles, minus 1.00 moles squared times 6.49, that's going to be liters squared times atmospheres, that's going to be over moles squared, and this is all over 22.4 liters. And the answer is, instead of the, what? What? Volume squared. Volume squared. We're talking about down here? You're right. Okay. Thank you. Okay, 0. You stay up here and do it every day. Okay? Yeah, it's easy. I know. Right. Yeah, it's really easy. Okay, 0.990 atmospheres. Okay? Okay, so you can see it went from 9 down to 0.990, so it's not a huge difference. But, you know, as you get up to higher and higher pressures, then you're going to see more and more deviation. And, you know, some of this rearranging is just, I'll hold it up there for a second, you guys can write it down. It's just a little bit tricky. But anyway, I think the important thing is, like I said, learning what it's about and how to apply it. Okay? But I will give you the equation. So there you go.